Our last topic of our third unit is called satellites. Does anybody know what a satellite is? Like we hear of satellites in the sky, right? What do satellites do? What are they? Yeah? Yeah, it's exactly what it is. A satellite is something that orbits around something else. The Earth is a satellite of the Sun. The International Space Station is a satellite of the Earth. The Moon is a satellite of the Earth. Right now, as I walk around this classroom, I'm a satellite of you because I'm orbiting around you. Having said that, most times we talk about satellites, we're talking about satellites in space that are held in orbit by gravity. There are two kinds of satellites. One's called a natural satellite. And a natural satellite is a satellite like, say, the Earth revolving around the Sun. It's there by nature. The Moon revolving around the Earth. Asteroids revolving around the Sun. Those are natural satellites because they occur in nature. But they behave the same way as artificial satellites, which do not naturally occur in nature. We've put them there. The International Space Station orbiting the Earth, the Space Shuttle up until a few years ago orbiting the Earth. Regardless of which type of satellite we're dealing with, we deal Now, just like planets, most satellites, natural or artificial, travel more or less in circular orbits. We know that planets take elliptical orbits, right? But they're almost circular orbits, held in place by gravity. That centripetal force, equal to the gravitational force. In other words, we would say that mv squared over r is equal to g m1 m2 over r squared. Notice I've conspicuously left off the subscripts for those masses. You'll see why in just a second here. What mass are we dealing with over here on the left-hand side? Is it the mass of the satellite or the mass of the central body? The thing that's being revolved around. If I swing my keys around, and I want to find the centripetal force using mv squared over r, what do I use for mass? The mass of my hand holding them in place, or the mass of the keys? You guys know the answer to this question. Come on. Liam, what's the answer to the question? It's the mass of the keys, right? So that the mass of the satellite, the thing that's doing the orbiting, is this m. Now, what about my other ones on the other side? One of them is the mass of the satellite. One of them is the mass of the central body. I'll just leave it with no subscript there. One's the mass of the satellite, one's the mass of the central body, or the thing that's being orbited around. Let's cancel out something here. Let's cancel out one r on each side. Let's cancel out the mass of the satellite. We're left with, over here, v squared, the r's disappeared, is equal to g times m over r. This m will represent the mass of the central body. Not the mass of the satellite, it cancels out. In other words, it doesn't matter how heavy the satellite is. You add payload to the satellite, it doesn't make any difference. It's going to orbit at the same speed, at the same altitude. Now remember, when you're using this equation, which by the way does not appear on your equation sheet, this appears, but the combination of them doesn't. When you're using this equation to solve for something, remember to deal with r. R is from the center of the central body to the center of the satellite. Center to center. If you're given the distance from the surface to the surface, add the radii. If you want to find the distance from the surface then subtract the radius of the Earth, or the radius of whatever planet that it is that's the central body. All right? Here's a question on page 278. It says, Earth's moon is this far from the Earth. That's a distance that we like because it's from center to center. You can see in the diagram. But we don't like the kilometer part of it. We want to convert that to meters. So I'm going to circle that to draw attention to it. We're going to find the orbital speed of the moon. I'm going to derive that equation again just so we get in the habit of doing it properly. Fc is equal to Fg. We're going to say mv squared over r is equal to gm1 m2 over r squared. One of the m's cancels. One of the r's cancels. I'm left with v squared is equal to g times m over r. What m do I have here? The mass of the Earth or the mass of the moon? What canceled out of this? What just disappeared? Yep. The moon's mass disappeared, right. So this is going to be the mass of the Earth. The mass of the central body, the thing that's being revolved around. So we're going to say V is equal to the square root of 6.67 times 10 to the minus 11 times the mass of the Earth divided by R, which is 3.844, times 10 to the 8 meters, because we've got to convert that kilometers to meters. Take a guess. Before we calculate this, what do you think we're going to get? Like a big number, a small number? 100 meters per second, 1,000 meters per second, 1,000,000 meters per second? Something in between? What do you think we're going to get at? Oh, I was looking at Riley and calling him Adam. Riley, what do you think we're going to get?
I'd say like a pretty fast number.
Yeah? Like what?
I don't know, like
100,000 meters per second? Yeah, it's pretty fast. 100,000 meters per second. Anybody think you think that's too high? Okay. It is too high. I'll tell you that now. It is too high. But it is pretty fast. We are going to get a pretty fast number here. Let's see exactly what we do get. We're going to say 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24. Divide that by brackets 3.844 times 10 to the 8. And the bracket, let's square root that. We end up getting a speed of 1,017, or we're going to say 1.01. 1.02 times 10 to the 3 meters per second. So not 100,000 meters per second, Riley, but 1,000 meters per second is still pretty fast, right? That's still about 3 times the speed of sound. Yeah? Yeah, it's 3.844 times 10 to the 5 what? Look what's after that. 3.844 times 10 to the 5 kilometers, and we want to convert it to, right. That's why we got 10 to the 8 there. All right? So 3 times the speed of sound. Why wouldn't we hear a sonic boom when the moon is whizzing past us at 1,000 meters per second? In order to have a sonic boom, you need air. Right? If something's flying past the speed of sound in space, there's no sonic boom because there's no sound. As the moon hurtles around the Earth at 1,000 meters per second, there is no sound, period, because there's no air to transmit that sound. Okay, I got 2 questions for you to work on page 278, please.